We've been hinting around this for some time now, but we've only really still looked at uniaxial stress states. But we need to really recognize that we're going to have to deal with much more complex stress states. So basically, stress states in multiple different directions, shear stresses, combinations of shear stresses and normal stresses. So we need to figure out a way of how do we actually calculate, if we're given a stress, how do we calculate a strain? If we have a strain, how do we figure out what the stress state was in our material? So this is where we're going to have to use those second rank tensors and apply them. But first we need an equation that can relate, these two. So one of the ways that you can do this is by thinking of this thought experiment. So for example, I am going to first pull in the 1-1 direction. So when I pull in the 1-1 direction, I'm going to have a strain in the 1-1 direction. Just imagine this is 2D, forget about 3D for a second. And then in the 2-2 direction, it should contract due to my Poisson's ratio. Now remember, if I pull in the 1-1 direction, my Poisson's ratio definition is going to be nu is equal to, again, minus my contraction, so E22 over E11. We've already defined E11 is equal to minus E22 over basically sigma 11 E, and when we flip those, you can get that expression for basically E22 here. In the second step, you would do the same thing for just uniaxial stress in the 2-2 direction. So when you do that, at the end, the total strain in the 1-1 direction will be this plus this, or sigma 11 minus nu sigma 2-2 all over E. Same thing for the 2-2 direction, this plus this. So you end up with these two equations. And you could expand this for 3 directions as well. Or the most important equation here, equation 98 in the notes so far, subject to change. This is our general expression for strain in a complex stress state. So epsilon ij, 1 over E, 1 plus nu, sigma ij, minus nu sigma kk delta ij. Delta ij is our Kronecker delta. It's going to be equal to 1 when I is equal to j and 0 when I does not equal to j. So for example, let's say I have that stress state that we saw above. So I have my cube, and then in that stress state I had stress in the 1 direction, 1-1, and then stress in the 2-2 direction here. So I have stress in the 1-1, I have stress in the 2-2. So let's just write out what would be the strain in the 1-1 direction. Well, looking at this equation, 1 over E times, I'll do it basically 1 plus nu times sigma 11 minus, now I is equal to j here, so this exists, so I have to sum over minus sigma 11 minus nu sigma 22 minus nu sigma 33. I see here that this minus nu sigma 11 is going to kill out this basically nu here, and what I'm left with is epsilon 11 1 over E times basically sigma 11 minus nu times sigma 22 plus sigma 33. But in this system, we don't have any sigma 33. So I'm left with an expression E11 is equal to, and actually I'm going to copy it here. Let's go ahead. I'm going to copy this. So let's go over here. So you see that these expressions are equal, right? Sigma 11 over E here, minus nu sigma 22 over E here. So this is our general expression. And we could write out every stress and strain like this. What about epsilon 1, 2? Well, in epsilon 1, 2, 1 over E times 1 plus nu times sigma 1, 2, because I still have to write that out. And what about the other one? I and j are now no longer equal. Hence, I'm just left with this. And this is a very important revelation. I cannot have a shear stress, or excuse me, a shear strain without the corresponding shear stress. So a normal stress can't induce a shear strain. But you can see here that I can have a strain in the 1-1 direction that is created, even if this was 0 and this was 0, there'd still be a sigma 3-3. I could have a strain in the 1-1 that's created by a stress in the 3-3, and that makes sense, because if I'm pulling in the 3-3, I know my material is going to contract in the 1-1. And you see that that would be a negative value anyways. So this is a critical equation. It's the most important equation. We're going to use this over and over and over in this class. And you can just, again, when I is equal to j, you could also pop on plus epsilon t delta t. Again, if you're doing normal strain, so plus epsilon t delta T would be added on here as well, but more into that later. You could write it out if you're used to basically working with basically a linear algebra approach. You could write it like this as well, but no pressure. You could relate G is related to equals E over 2 times 1 plus nu. You can kind of deduce that if you just kind of work through the math here. And then if you have hydrostatic stress, you can kind of plug that in here. So this is all good, but let's actually do an example to kind of bring this home. So I am working to make a cufflink made of steel. So I have my coordinate system here. Steel, I know my Young's modulus should be about 200 for steel, but for metals, GPa, nu is equal to 0.3. Simple channel does not constrain the metal in the one direction. Well lubricated, so frictional forces and stresses along the channel walls can be 0. And I need to write out what are all the what are all the stress components here. Well, let's go ahead and let's write out what stresses exist in this system. So basically, initial thickness of 6 millimeters, I need to go to 3 millimeters. So I already know that in the 3-3 direction, it's going to exist. There will be some strain in the 3-3. And that strain in the 3-3 will just be equal to, what's my final dimension? 3 millimeters minus my initial dimension, 6 millimeters, divided by my initial dimension, 6 millimeters, and that's equal to minus 0.5. So I've got my strain in the 3-3. Good. I'm going to also have a stress in the 3-3. Perfect. Will there be a strain in the 2-2 direction? Well, I push this material down. It wants to expand out, but I've got the rigid wall here. So I'm not going to have a strain in the 2-2, but again, the material wants to expand out because it's a metal, so I will have a stress in the 2-2 because there's a force exerting against there. What about in the 1-1 direction? No, it's going to expand freely. So this should be positive here, and there will be no stress here because there's no stress, there's no force on it. And because it's well lubricated, there's no shear stresses, so there's no shear strain as well. So I've got basically an equation, 3 unknowns. I can solve it in my handy dandy Mathematica. So let's go ahead and let's solve this problem. So I know that my E, or my Young's modulus, is equal to 100 times 10 to the 9. I know that my nu is equal to 0.3. I know that my E33 is equal to minus 0.5. And that's all I need to know. And I know that my E22 is equal to 0. And I know that my sig11 is equal to 0. And that's it. Now I'm going to solve three unknowns. Means I need 3 equations. E11 is equal to what? 1 over y times sig11 minus nu times sig22 plus sig33. And I'm going to copy this. 3 equations. I know E22. So this should be sig22, 1, 1. This should be 3, 3. This should be 3, 3. This should be 1, 1. And I'm solving for what? I'm going to solve, note the double equal sign in case you have any mathematical errors. I'm solving for E11, sig22, sig33. Does this make sense, at least qualitatively? E11 is positive. Yes, it should be expanding in the 1-1 direction. My stress in the 2-2 should be negative because it wants to expand, but it's not. Voila. And then sig33 is negative because it should be negative there. Great. So now, next time we're going to go into a very special stress state, thin wall pressure vessels, and then we're going to call it basically a day. So we'll see you next time for thin wall pressure vessels. Very special stress state. See you next time. Bye.